Welcome to session 1, which is on number systems and codes. Many number systems are in use in digital technology. The most common are the binary and hexadecimal number systems. These number systems are defined as functions in the same way as in digital systems. The physical quantities can assume only discrete values. So at the end of the session, you should be able to understand the binary number systems, its similarity to the decimal system, how to convert from binary to decimal and vice versa, apply arithmetic operations to binary numbers, determine the ones and twos complements of a binary number. What key topics shall we cover? We'll cover the decimal number system, or you should learn or know about the decimal number systems, but binary number systems, how to do the conversion from decimal to binary, conversion from binary to decimal, how to do binary arithmetic operations. You will learn about ones complement and twos complement. The reading material is from chapter 1 of your recommended test, Fundamentals of Logic Design, and chapter 2 of Digital Fundamentals, the book on digital fundamentals. So, number systems. We are used to the decimal number system. These are made up of decimal digits, which are 0, 1, 2, up to 9. But how many items does a decimal number system represent? How do you do that? If you write a number like 8,653, what really does it mean? You realize that if you say 8,653, every digit in that number actually has a weight. The position counts. So there is a ones unit, the tens unit, the hundreds, and then the thousands, and so on and so forth. So what you really mean by saying that 8,653, what you mean that there are 8,000s, there are 600s, there are 5 tens, and there are 3 ones or 3 units. So that is the number 8,653. That is what it actually stands for. But what about fractions? How do you represent the fractional part? Well, it only means that instead of you have a tens and the hundredths of that. So a number like 97,654.35, we are interested in the decimal aspect. So the 0.35, it means there are 3 tenths and then 5 hundredths, right? This number formally will represent as we'll write a 10 subscript to the number. But because we used to the decimal number system, we normally would omit the subscript of 10. Why do we use 10 digits anyway? Is it probably because we have 10 fingers? But there are cultures in which they don't use the decimal number system. There are many cultures. You can find out what cultures use a different number system. So we are saying that the most commonly used number system has 10 digits. Yeah, it's got 0, 1, 2, up to 9. So those are 10 digits, or the base 10. To your left, if you write down any number, first you have the units, there's a tens, the unit singles, then you have the tens, the thousands, and it increases in powers of 10. So 623 would mean 600, that's 6 times 10 to the power of 2, 2 times 10 to the power of 1, and 3 times 10 to the power of 0. Right. So you have increasing powers of 10, and then you can also have decreasing powers of 10, which will take you to the decimal values. What it means is that we can actually represent a number like 953.78 as 9 times 10 to the power of 2 plus 5 times 10 to the power of 1 plus 3 times 10 to the power of 0 plus 7 times 10 to the power of minus 1 plus 8 times 10 to the power of minus 2. In general, if you're given any number, n, which is represented as a, let's say a4, a3, a2, a1, a0 point, a minus 1, a minus 2, a minus 3, right, to base r, you can then represent that number as a for a subscript 4 times r to the power of 4 plus a subscript 3 times r to the power of 3 plus a subscript 2 times r to the power of 2, and so on. So that's a general representation of numbers. So, how do binary numbers differ from our digital systems? In binary systems, we have only 2 digits or 2 bits or 2 numbers that we use to represent. That's 0 and 1. Now, then some of you would ask that if we only have 2 digits, that we use to represent number, how then can we represent huge numbers? In the decimal number system, we're using 10 digits, but in the binary, we're only using 2. But also, why should we use 2? Why are we using only 2? Well, the reason is simple, right? Because if you want to design a device, to keep some information for you, it is difficult to think of any material which occurs in nature that can be in several states. That can be in several states, let's say 10 states. Right? It's difficult to think of anything of that nature. So, well, if you think of, say, water, you know that water can have 3 states, and those are, like it can be a solid state, liquid state, and, vapor state. But really, how are you going to use water to, represent anything on a machine, like a computer, But then, if you take like a light bulb, you can either switch that light bulb either on or off. So switching that light bulb on can be your 1, and switching it off can be your 0. So then, you say, okay, if I have a number of light bulbs, then I can put so many of them together, and by switching some of them on and off, I can really represent anything I want to. Right? So, how do we then represent some numbers? Let's say you take 1011. So, in a binary system, the highest digit you have will be a 1. So, you only have zeros and ones. To distinguish between the binary number system and any other number system, we have to write down the base. So, 1011 subscript 2, that's base 2. What this really means is that you have the 1 on your leftmost as 1 times 2 to the power of 3 plus 0 times 2 to the power of 2 plus 1 times 2 to the power of 1 plus 1 times 2 to the power of 0. Now, if you did perform these calculations, you realize that, okay, that actually works out as 11 because 2 to the power of 3 is 8. 0 times any number will be a 0, and then you then have what? 2 to the power of 1, which is 2, so 8 plus 2 is 10, and then 2 to the power of 0 is a 1 times a 1 is a 1 plus 10, that gives you 11. So the number you have as 1011 base 2 is actually equivalent to 11 in base 10. The same way, you can convert fractions. So fractions will be 2 to the power of minus 1 and 2 to the power of minus 2. We can group. Normally, we tend to group the bits. We tend to group the bits, put them into groups of 8, call a byte, And then, of course, we have half of that, we call it a nibble. So 4 bits, we call a nibble. So the byte is one of the, units that we use. And of course, this is a term that you've come across several times, you store this in bytes, so you have your memory, your disk space, you measure in kilobytes, and so on and so forth. So a byte is just a group of what? 8 bits. And a nibble is a group of what? 4 bits. So, to recap, digital devices will only use binary number system, which consists of zeros and ones. The base is 2 for this system, right? So you have a binary point, and you have decreasing powers of 2 and increasing powers of 2. This is a concept that you need to what? Fully appreciate if you are to go further. So, why do we use binary numbers? I've said it already. It's easy to represent zeros and ones using electrical values. So something can either be on or off. You can have a switch on or off. It's also possible to tolerate noise if you use binary numbers. It's also easy to transmit the data, and of course, it's easy to build the binary circuits. So if you look at the diagram on your left of a binary signal, you see that there is the first block from 0 to 1, which would be a range for logic 0, and then from 3 to 4 will be the range for logic 1. Anything in between, you discount, right? Now, we can use these digits to build logic gates. An example of a logic gate, what we call an AND gate, is shown on your right. You see that diagram with an input of 1 and a 0. Of course, we'll learn about this logic later, but if you have a 1 and a 0, yeah, the output will be a 0 because it's an AND gate. Both of them must be true for the output to be true. How do you convert between numbers, the number bases? Well, you need to do things in a certain way. So if you have a decimal number, you first convert that into a binary number. And then if you want to convert that then into an octal number, where you can do that conversion, and then you can convert the binary number also into a hexadecimal number. So in other words, what you need to understand is that your number conversion must be done in a certain logical way. It's easier for you to convert a binary number to a hexadecimal by first converting it into what? A binary number. And same way, it's easier to convert a decimal number to an octal base, yeah, by first converting it into what? A binary number. Now, how do you actually convert a whole number from decimal to another base? Let's say base 2. Well, it's a matter, there are a number of procedures, one is called the repeated, division, where you repeatedly divide by 2. So, for example, you have 13, and then you want to convert that into a base 2 number. So you divide 13 by 2, which gives you a 6, a remainder, a 1, and then you divide the 6 then by the 3, by 2, that gives you a 3, remainder 0, and then you divide the 3 now by 2, which gives you a 1, remainder another 1. And then if you divide the 1 by 2 now, well, if you can't divide it, so that's a 0, and then a remainder 1. So in reverse order with your remainders, you get a 1, 1, 0, 1, which would be your 13. Another way to do it is to the weighting system, where you write down powers of 2 from 0, 1, 2, so 2 to the power of 0, 2 to the power of 1, 2 to the power of 2, 2 to the power of 3, 2 to the power of 4, and so on. And then you look for the highest number that 13 can contain. So, and then write a 1 underneath that, and so on. To convert a fraction to another base, we do the opposite of converting an integer. That is, you do repeated multiplication. So if you have, for example, 0.625, you repeatedly multiply that by 2. You get an integer part and a fractional part. So if you multiply that, you get 0.625 by 2, that gives you 1.25. So the 1 becomes your integer part. Then the fractional part, you then again multiply that by 2, and then you get 0.50, and you multiply again by 2, and you get 1.0. So in again, in the order in which you got them, that gives you 0.101.